So here we look at our final two groups of nucleophiles that we can add to aldehydes and ketones, and those being alcohols as well as amines. So when it comes to alcohols, we're going to focus on the 1,2 addition. Alcohols are capable of doing 1,4 addition, but it's not a commonly used or very important reaction in most situations. So what we're going to look at primarily here is the 1,2 addition. And in the case of an aldehyde or ketone, again, doesn't matter which one we're using here. We do this in the presence of an acid catalyst. We actually have a couple different products that we can form. We can get one addition of the alcohol that gives us a product like this. Or we can end up with a second addition, such as that. And which one we get all depends on the reaction conditions. Um, the names for these are, the middle one here is known as a hemiacetal or a hemiketal, and the one on the right is known as an acetal or a ketal after two additions. Whether we call it a or an acetal or a ketal all depends on what the starting material is. If we start from an aldehyde, then typically we refer to them as hemiacetals and acetals, and ketones would yield hemiketals and ketals. So how does this reaction work? Well, it's going to have a lot of mechanistic similarity to many of the other reactions that we've already covered in this section. We know that under acidic conditions, that the first step will often be, and this is no exception, protonation of the carbonyl. Why does this happen? Well, as we've seen before, this happens because while the carbonyl is a good electrophile, by protonating it, we make it even better. And by making it even better, we can use weaker nucleophiles, such as alcohols. And so now that we've done that, our alcohol, which we'll use methanol in this case, adds in, and we push the electrons up onto the oxygen. From here, we lose a hydrogen, and that gives us our hemiacetal, or in this case, because I started with a ketone, this would be our hemiketal. Now, in certain situations, the reaction will stop here, and in a few minutes, we'll talk about a very, very important biological example of this type of reaction that does stop at this point. However, in other situations, the reaction will keep going. And to keep going, our OH group gets protonated again. And then the oxygen from what was the alcohol adds in its lone pair and kicks out water. Now, the intermediate we form here is a little bit different than what we had previously. although it bears a lot of similarities. And by similarities, I mean between these two intermediates. So both of them are carbons double bonded to oxygens. It's just one of them has a hydrogen attached. The other one has some sort of R group. This one being methyl because we started with methanol. Had we started with a different alcohol, that could be a very different group. But the key point here is it's still essentially a carbonyl with an extra group on it that makes it positively charged and makes it good for nucleophilic attack. So now a second molecule of the alcohol can attack. Electrons move up onto oxygen. Gives us that intermediate, which then loses a proton to get to the product. Now, you notice every step in this reaction pathway is reversible, and every step here is completely reversible. And so this becomes a reaction that you can control only on the basis of Le Chatelier's principle. And the main piece that you use to control it is right here, is water. So we're kicking out water in this step. So water is one of our products. So we can favor our products